Welcome to Chapter 4, Energy Analysis of Closed Systems. This is where thermodynamics starts to feel more practical. Everything you see around you, engines, refrigerators, batteries, relies on energy moving around inside closed systems. This chapter will teach you how to track and balance that energy like an accountant tracks money. We'll break down key concepts like the First Law of Thermodynamics and apply it to simple, real-world systems. Think of it as understanding the income and expenses of energy inside a system. By the end of this session, you'll be confident in writing and solving energy balance equations for any closed system. Let's get started. 1. Moving boundary work. Let's talk about moving boundary work. This is the type of work that happens when the boundary of a system moves, like in piston-cylinder devices during expansion or compression. It starts with a simple idea. If the boundary moves, work is done. The formula is written as WB equals the integral of PdV. This just means we calculate the area under the pressure-volume curve. Next, we follow a clear sign rule. If the volume increases, it's expansion and work is positive. If the volume decreases, it's compression and work is negative. There are also shortcuts for common processes. For constant pressure, it's just pressure times the change in volume. For polytropic processes, there's a formula with pressure, volume, and an exponent, n. For ideal gases and isothermal processes, it uses mass, gas constant, temperature, and the log of volume ratio. This slide helps you recognize how to quickly calculate work depending on the type of process in closed systems. 2. Energy balance for closed systems. Let's go over the heart of thermodynamics, energy balance for closed systems. Everything starts with the first law of thermodynamics, which is just energy conservation. Energy can't be created or destroyed. It simply moves in or out of the system. The equation is clear. Energy in minus energy out equals the change in energy of the system. Now, how does energy transfer happen? It happens through two main channels: heat transfer, which we call Q, and work transfer, which we call W. On top of that, there's the change in stored energy, like internal energy, kinetic energy, and potential energy. Sometimes we want to see this balance on a per-unit mass basis, so we divide everything by mass and use lowercase letters. Other times, we care about how fast energy is moving, so we use the rate form with respect to time. This simple balance helps us understand and predict how energy flows in everything from engines to power plants. That's why it's the foundation of all energy analysis. 3. Specific heats. Let's talk about specific heats, a simple but powerful concept in thermodynamics. Specific heat tells us how much energy we need to raise the temperature of a substance. There are two main types. First, we have specific heat at constant volume, called CV. This is the energy required to raise the temperature when the volume stays fixed, like heating gas in a sealed, rigid container. Then, we have specific heat at constant pressure, called CP. This is used when the pressure stays constant, like heating air in an open room. For ideal gases, there are a few shortcuts. The enthalpy, H, is equal to internal energy plus pressure times volume. Also, CP is always bigger than CV, and the difference between them is simply the gas constant, R. Finally, whenever we want to calculate how much energy changes when temperature changes, we can just integrate CV or CP over the temperature range. This way, you'll always have a quick method to estimate energy changes with temperature, depending on whether your process is constant volume or constant pressure.
4. Internal energy, enthalpy, and specific heats of ideal gases. Let's simplify things by focusing on ideal gases. For ideal gases, life is easy because their properties depend only on temperature. That means when temperature changes, internal energy and enthalpy change. Simple and predictable. Internal energy is written as U equals U of T, and enthalpy is H equals H of T. This tells us both properties are just a function of temperature. For small temperature intervals, we don't need complex calculations. We can approximate changes in internal energy and enthalpy by multiplying the average specific heat by the temperature difference. Delta U is roughly CV average times T2 minus T1, and delta H is roughly CP average times T2 minus T1. But sometimes gases aren't ideal, especially at high pressures or low temperatures. That's where the compressibility factor Z comes in. It helps us correct for real gas behavior using the formula Z equals PV over RT. This way, you can confidently handle both ideal and non-ideal gas scenarios without getting stuck.
5. Internal energy, enthalpy, and specific heats of solids and liquids. Let's look at solids and liquids. These substances are much simpler to handle because we treat them as incompressible. That means their specific heats at constant pressure and constant volume are practically the same, and we just call it C. For internal energy, it's very straightforward. The change in internal energy equals C times the temperature difference. No need to overthink it. For enthalpy, we add just a little more. It's the change in internal energy plus the product of specific volume and the pressure difference. Since solids and liquids don't expand much with pressure, calculations are simple, and you won't need to worry about complex variations. This makes energy analysis for solids and liquids much faster and easier than for gases. 6. Biological systems. Let's finish by exploring how thermodynamics applies to our own bodies through biological systems. Metabolism is simply the energy conversion happening in living organisms. Even at rest, our bodies burn energy. That's called the basal metabolic rate, or BMR. And for an average 70-kilogram person, it's about 84 watts, like a small light bulb always running. Food gives us energy, and it varies by type. Carbohydrates and proteins give around 4.1 kilocalories per gram, while fats pack more energy, around 9.3 kilocalories per gram. When it comes to weight loss, there's a helpful rule of thumb. Burning 1 kilogram of body fat equals about 33.1 megajoules, or 9211 kilocalories. From this, we can estimate how much daily calorie deficit we need to lose weight over time. And to keep track of health, we have BMI, or body mass index. It's simply weight divided by height squared. It's a basic but quick way to check if we are within a healthy weight range. Thermodynamics doesn't just power machines, it powers us too.